Hello everyone, myself Dr. Snehalata Reddy, Assistant Professor of Physics, Pingal Government College for Women, Warangal. As part of paper 5 electromagnetism, BSc for BSc, we are into the new topic, new unit, magnetostatics. So what is magnetostatics? Magnetostatics is the study of magnetic fields produced by steady currents. So, as we discussed in the previous unit, that a static charge produces a field around it. That field is electric field, and the intensity of the electric field represented by E. We have discussed many laws regarding the electrostatic fields. So here in magnetostatics, we deal with the moving charges. Here the motion of electrically charged particles gives rise to magnetism. So here we deal with the magnetic fields arised out of the steady currents. Here the steady current is nothing but it's an electrically charged particle. The motion of an electrically charged particle gives rise to magnetism. So before going into the details of the magnetism, magnetostatics, let me first let you know the concepts of magnetism, like magnetism, the bar magnet, the properties of magnet, magnetic field lines, magnetic field intensity, and magnetic field, the concept of magnetic field and its units. Here, before going into the details of this, let me first know you what is magnetism. So magnetism, the term magnet was first coined in around 600 BC when shepherds in an island named Magnesia in Greece were roaming about, grazing their sheep. They felt like some thing is attracted to their shoes, and this property of attraction led to the invention of led to the observation of this magnetism. So there the property of attracting materials, some materials, is known as, is termed to be as magnetism. So magnetism is the property of a particular type of materials which possess the property of attracting other materials. So the material which attracts other materials is known as a magnet, and the materials which are being attracted by this magnet are known as magnetic materials. In general, we know that iron, cobalt, nickel are the materials which are being attracted by magnet. There are some other materials. Generally, the magnetic materials are classified into diamagnet, paramagnet, and ferromagnetic materials. Depending upon their properties, different types of materials shows different types of properties. They are classified like that. Now the materials which are not attracted by magnet are known as non-magnetic materials. Wood, paper, plastic, these are some materials which are not attracted by magnet. So let me say some properties of magnets. this is a bar magnet shown in this figure. So this magnet has two poles. One is north pole and another is south pole. North pole is denoted with N and south pole is denoted with S. So this is a bar magnet. It is a material which shows the property of attraction. So in order to show the property of attraction, a small activity is being shown here, and for this a bar magnet is needed and some iron filings are needed. So here when a bar magnet is placed in heap of iron filings, then the iron filings are arranged in a particular manner as shown in this figure, and the iron filings are cling at the poles. A huge amount of iron filings are cling at the poles rather than at the surroundings of the bar magnet. So this shows that materials like iron, cobalt, nickel are attracted by the magnet. This is one of the properties of the magnet, which is its attractive property. So here one thing I would like to say, the iron filings are hugely cling to at the poles of the magnet. So here we have to understand the concept of pole strength. Pole strength is the ability of the poles of the magnet to attract magnetic materials. It is the ability to attract. It is the property of it is a more pole strength is at the poles of the magnet. The strength of the poles to attract magnetic materials is known as the pole strength. So here the pole strength is generally denoted by small m, and the units of the pole strength are ampere meter. Now here we can also say about magnetic moment. So what is magnetic moment? So magnetic moment is the nothing but the product of the magnetic length and pole strength gives you the magnetic moment. So it is denoted by capital M, and capital M is equal to 2Lm. So 2L is the length of the magnet and small m is the pole strength. The product of the length of the magnet and pole strength is magnetic moment, and the length of the magnet here is the distance between the two poles, north pole and south pole. That is denoted by 2L. So 2L is the length of the magnet. We say it is the distance between the two poles as to be 2L. So the product of the length of the magnet and the pole strength gives you the magnetic moment, and this magnetic moment is nothing but the force due to the external currents also, which produces a mechanical moment. So that we study in the further topics. I'll explain it in a clear manner in further topics where we also associate torque with it. Not only the magnetic moment is associated with a magnet, it is associated with a bar magnet, it is associated with the electron, it is associated with the electric currents, it is also associated with the magnet earth. So now the units of magnetic moment are ampere meter into the length of the magnet is of units meter. Therefore, it is pole strength is ampere meter and length is meter. Therefore, it is ampere meter square. The magnetic moment is denoted with the capital M and the units are ampere meter square. Capital M is equal to 2L into small m. 2L is the length of the magnet and pole strength, the product of the length and pole strength gives you the magnetic moment of that bar magnet, and the units are ampere meter square. Here are the list of the properties of the magnet. Here just now we have seen the simple experiment of attractive property, wherein the magnet attracts some materials like iron, cobalt and nickel, that is shown with this small activity, right? And next, this is attractive property. So magnet attracts ferromagnetic materials, these are. So such type of property magnet is exhibiting is known as attractive property. And the repulsive properties. What is repulsive property? Magnetic poles repel each other. Like poles repel each other and unlike poles attract each other. Like poles, for example, if a north pole of one magnet is brought near the north pole of another magnet, then there occurs a force of repulsion. Those two magnets repel each other. If a north pole of one magnet is brought near the south pole of another magnet, then they tend to attract. So this is the repulsive property. That means like poles repel and unlike poles attract each other. One more property is the directive property. So this directive property, whenever a bar magnet is suspended freely by means of a thread or anything, a string, then it always points towards north-south direction. North pole of the magnet points towards the geographic north, and the south pole of the magnet points geographic south. This is the directive property. So here one thing I would like to say, here the bar magnet which is shown here, if you divide this magnet into any number of pieces, for example if you divide it into two halves, then again you get two poles, one north and another south for one half, and for other half also the two poles exist. So always a magnet exists with two poles. Single pole is not possible. Single pole doesn't exist for a magnet. As in the case of static electric charge, we have seen in electrostatics that single positive charge is possible, single negative charge is possible, and the electric lines are radially outwards for a positive charge and goes up to infinity, whereas for a negative charge the electric lines of force are radially inward from an infinity. So here single pole doesn't exist, as unlike our electrostatics. In electrostatics, isolated positive charge is possible, so or isolated negative charge is possible, but single north pole or single south pole is not possible. Always magnetic poles exist in pair and a single pole doesn't exist. So if you cut into pieces, the maybe the intensity or maybe the magnetic effect is lessened, but the poles are not being separated, so they always exist in pair. So this directive property, as we discussed, whenever a magnet is freely suspended, it always points the north-south direction, north pole showing the geographic north and south pole of the magnet points towards the geographic south. So depending upon this directive property of the magnet, magnetic compass has been designed in order to show the direction of the in case of navigation. This magnetic compass is majorly used. So here the north pole is denoted with red and the south pole is denoted with blue. So depending on based on this directive property of the magnet, a magnetic compass is designed. So here you can see the repulsive property. Unlike poles attract each other, unlike poles attract and like poles repel. This is wrongly shown. Like poles repel each other, whereas for a bar magnet it is the magnetic lines of force are shown like that. Red one is north pole and this is blue is south pole, and the magnetic lines of those are the proper arrangement of the field lines. Those are nothing but the magnetic field lines. So those are shown like this. And let us know what is a magnetic field line. Like the magnetic electric field line, electric field lines starts from a positive charge, and they for a single positive charge they will be radially outward, and they start at positive charge and end up with a negative charge. But those are not closed loops. Those are electric lines of force, or the one starts from positive charge and end at negative charge, whereas this magnetic field lines are the continuous closed loops. These are continuous closed loops, and magnetic field lines are visual. We can visualize the this magnetic field lines. These field lines can be visualized. So these are visual realization of magnetic field. So magnetic field lines are nothing but the visual realization, visual intuitive realization of magnetic field. And here the magnetic field lines are shown. See here, north pole and south pole. Here the magnetic field lines originate at north pole and arrive at south pole. So here, and inside the magnet, the magnetic field lines move from south to north pole. So here we have to discuss some properties of the magnet field lines. As in the case of electric field lines we discussed, here the magnetic field lines, the electric field lines are imaginary field lines. Unit positive charge followed, the path followed by unit positive charge is an electric field line. Or here the magnetic field lines are the continuous closed loops, and they are the where they can be visualized like this of the magnetic field. So here as we see the, if we see the properties of the magnetic field lines, if you draw a tangent to any magnetic field line, the direction of the tangent shows the direction of the magnetic field B. Magnetic field is denoted by B. So the magnetic field direction is shown by a tangent drawn to the any magnetic field line. So here also we can say that the more are the number of magnetic field lines, the dense is the magnetic field, more is the magnetic field. If the magnetic field lines are less, we can say that the magnetic field is less. So here also the two magnetic lines, field lines, never intersect, because at the point of intersection the magnetic field has two directions, which is not possible. So no two magnetic lines, field lines intersect. And this is one another figure, the same thing we have discussed just now. The magnetic lines of force are closed continuous curves, and outside the magnet their direction is from north to south, and here the magnetic field lines originate from north and arrive at south. So it is outside, it is north to south, and inside the magnet it is from south to north pole. So here let us see what is this magnetic field intensity and magnetic field induction. So magnetic field, what is magnetic field or magnetic field induction? Let me say that the space around the magnet in which the attraction occurs is nothing but magnetic field. So magnetic field is nothing but the space around the magnet. It is the region around the magnet wherein the attractive the force another material experiences an attractive force. The field around the magnet wherein the magnetic material experiences an attractive force. So that field we describe it as the magnetic field. So apart from this magnetic field, this magnetic field intensity is also we see here. So in case of electric charge, static charge produces only field around it is electric field, the intensity of that field is electric field intensity E. Here the magnetic field intensity H is not the intrinsic property of the material of the magnet. So the natural property of the magnet is the magnetic field around it. So B is magnetic field induction is the region around the magnet is magnetic field, whereas the magnetic field intensity is due to the moving charges, the electric currents, but it is not the intrinsic property of that magnetic field intensity is due to electric currents, and the magnetic field induction is the intrinsic property of the magnet which produces the field around it. That field is magnetic field induction B, whereas H is due to the electric currents. The relation between B and H here is B is equal to mu H, where mu is the permeability of the medium. For free space, we can say that magnetic field induction B is equal to mu naught into magnetic field intensity. So here mu naught is the permeability of the free space. Mu naught is a factor, a physical factor which governs the magnetic lines of force to pass through it, or it is the physical factor which governs the magnetic field lines to conduct through that medium. So it is the physical factor, mu naught is the factor which governs the magnetic lines of force. So the value of mu naught is 4 pi into 10 to the power of minus 7 Newton per ampere. And here the concept of magnetic field I would like to. So here, if you consider a positive test charge and it is moving in a magnetic field with a velocity v through a point P. A point P is in magnetic field, and now a positive test charge Q is moving with velocity, and here the force is experienced, is deflecting sideways, so it experiences a deflection force sideways. Then the magnetic field induction B at point P is defined as F is equal to Q naught V cross B. So from that I can write B as equal to F by Q naught V. So here Q naught is the positive test charge, and it is moving with velocity V. So the force, deflecting force experienced sideways is F. So the magnetic field is defined as the ratio of the, so as this is a cross product, I can write it as Q naught VB sin theta. F is equal to q naught VB sine theta. That becomes the magnitude. B is F by Q naught V is magnitude. So if I write the magnitude as equal to F is equal to Q naught VB sine theta, then from that I can write B as equal to F by Q naught V sine theta. So here I can define the magnetic field induction as the ratio of the force. It is the ratio of force on moving charge at a particular magnetic field induction at a point is due to the magnetic force exerting. So I can define this magnetic field induction as the magnitude of the magnetic induction at a point is the ratio of the force on a moving charge at a point and the product of the charge and velocity component along the direction normal to the induction. So it is the ratio of the force to charge and the component of the velocity along a direction normal to the induction. So B can be written as F by Q naught V sine theta. So here I can say the magnetic field as to be if unit charge of north pole of unit pole strength, the force experienced by a north pole of unit pole strength is magnetic field induction. In that way also the magnetic field induction is defined. So if a north pole of unit pole strength is taken and the force experienced by this unit force experienced by north pole of unit pole strength is nothing but magnetic field induction. So there I write B, magnetic field induction B is equal to F by M. So F is magnetic force experienced by north pole of unit pole strength. So B is equal to F by M. If M is unit 1 ampere meter, then the force experienced by this north pole of unit pole strength is nothing but magnetic field induction. So B is equal to F by M, or F is equal to, I can write MB. From that I can say the units of magnetic field induction B is equal to, just now we have found out the expression for magnetic field as F by Q naught V sine theta, and hence the unit of B is given by force unit is Newton, and charge it is Coulomb, meter per second is the velocity. So Newton Coulomb per second comes to be ampere. So it is ampere meter. Coulomb per second is charge per time, that is current. So it is ampere. So Newton per ampere meter is the unit of magnetic field induction. So here we can also see that the force have the units of Newton, ampere meter is the unit of pole strength, therefore this is F by M. So just now we have also defined magnetic induction as force experienced by north pole of unit pole strength is nothing but magnetic field induction. So from that also I can write Newton per ampere meter as force per magnet unit pole strength. So MK's unit is Weber per meter square. This Newton per ampere meter can be written as Weber per meter square, or it is Tesla. So Tesla is the MK's unit of SI unit of magnetic field induction. So Weber per meter square is nothing but ampere Newton per ampere meter, and in CGS unit of magnetic field induction is Gauss. So here we have to remember that 1 Weber per meter square is equal to 10 to the power of 4 Gauss. So these are the some pictures of sources of magnetic field. So the first one is a current carrying wire. So the current carrying wire, the field around it is magnetic field. So magnetism is nothing but the uh, uh, it's a phenomena produced due to the flow of electrically charged particles. So it is this is first observed by Oersted, which we discuss in this. It's a simple experiment we discuss in the next video lecture. And here the sources of magnetic fields are due to loop of wire. This we shall discuss in the next lectures. Solenoid produces magnetic field around it. Loop of wire produces magnetic around it, maybe it is a circular loop. And bar magnet produces magnetic field. And planet earth is a huge magnet, it also produces magnetic field. So these are the some sources of magnetic field. So tomorrow, next class, we shall discuss about the Oersted experiment, which leads to two important laws like Biot-Savart law and Ampere's law in magnetostatics. Thank you.